Quality control of radiopharmaceuticals. Quality control of Tech-99 eluate. Moly breakthrough is the radionuclidic purity. Alumina breakthrough is chemical purity. There's also radiochemical purity. Radionuclidic purity. We are looking for the presence of Moly-99 in our eluate. As we elude the generator, we get Tech-99M off of the column, and a small portion of Moly will come with it, the Moly-99 breakthrough. We put the eluate in a special pig and assay it in the dose calibrator. The pig will absorb all the Tech-99M energy and allow the Moly-99 energies to be detected by the dose calibrator. The limit is no more than 0.15 microcurie of Moly to millicurie of technetium. One thing to keep in mind is the technetium-90 decays, the ratio of Moly to Tech-99 will increase. Too much Moly will interfere with our study and expose the patient to the higher energy levels. The Moly breakthrough, the limit is 0.15 microcuries per millicurie of Tech at time of administration. Need to determine only for the first elution. It is measured by detecting 740 keV photons in a dose calibrator. You need to block out the 140 keV photons from Tech by thick shielding. Ratio increases with time. Calculating the time of exposure. The time is equal to negative ln multiplied by the initial activity of Moly divided by the initial Tech activity, all over 0.105 minus 18.07. The alumina breakthrough originates from alumina column of the generator, interferes with the preparation of Tech sulfur-colloid and labeling red blood cells. The limit is 10 micrograms per ml of Tech. Test kit used to determine the amount of alumina when compared to a standard. Alumina breakthrough continued. Since the Moly-99 column is made up of alumina, there is a possibility of alumina contamination in our eluate. A small drop of the eluate is put on a special type of paper, like a litmus, alongside a drop of a standard, which contains 10 micrograms of alumina plus 3 per ml. The pinker the eluate, the more alumina is in the solution. This is important since alumina will interfere with binding. Physicochemical tests. Physical characteristics. pH and isotonic strength. The ideal pH is 7.4 for blood. Radionuclidic purity and radiochemical purity. Physical characteristics. Look at the color and state of the radiopharmaceuticals. Colloidal preparations should have a proper size range. Technetium-99M sulfur-colloid should be between 0.1 and 1 micrometer. Check size through a microscope. Proper size localizes in liver, whereas larger particles will go to the lungs. Technetium-99M MAA should be between 10 and 100 micrometers. Check size using a hemocytometer under a light microscope. Particles larger than 150 micrometers should be discarded. Also take note of number of particles, which can be determined by counting the particles under the microscope. You can see here in the image how to count the cells, which cells are counted and which ones aren't. Radiochemical purity. Fraction of the total radioactivity is in the desired chemical form in the radiopharmaceutical. Arise from decomposition due to solvent, pH, light, and etc. Examples include free protectanate and hydrolyzed technetium-99M. These impurities cause poor quality images and gives unnecessary dose to the patient. Methods of detecting the radiochemical purity is precipitation, TLC, which is thin layer chromatography, gel chromatography, gel electrophoresis, ion exchange, solvent extraction, high performance liquid chromatography, and distillation. TLC, thin layer chromatography, the most commonly used form of radiopharmaceutical QC. Most radiopharmaceutical kits are prepared using technetium-99m. The technetium-99m becomes attached to a substrate molecule in the kit, called a ligand, designed to localize in a specific organ system. Most of the technetium-99m should tag to the ligand for the radiopharmaceutical to be efficient. Very little free tech should be present in the final product. Hydrolyzed reduced Tech-99m, another byproduct of tagging process, should also be present in low levels. Both free and hydrolyzed reduced technetium-99m can give artifacts on scans, which may mislead diagnosis or make assessing scans difficult. The USP has set the minimum tagging efficiency standards for most radiopharmaceuticals. Each radiopharmaceutical compounded must be tested for radiochemical purity before use in patients. Unless the radiopharmaceutical is sufficiently tagged, the accuracy of the patient diagnosis may be compromised. Counting devices used: multi- and single-channel analyzer, developing media, which is Whatman paper strip or ITLC, instant thin layer chromatography strips. Solvents are 85% methanol acetone, methyl ethyl ketone, and 9% normal saline and water. Strip preparation. Chromatography kits contain pre-cut strips of appropriate size and media. Cut 8 cm long and 1 cm wide strips. Lightly draw a line 1 cm from the edge of the strip. This is the origin, or the bottom, where the sample will be spotted. Draw a second line 3 cm from the bottom of the strip. This is the cut line after the strip has been developed. Using a solvent-soluble ink, lightly dot the ink 7 cm from the bottom of the strip. This is the solvent front. Store prepared strips in a tightly closed container in a moisture-free environment. Here we see on the image where the bottom is, and then the origin. You apply 2 adjacent drops of the sample. You cut in the center and solvent to the top. Developing procedure. Place enough solvent in the developing chamber to just cover the bottom. Using a syringe with a small needle, spot the sample on the pencil origin line. Immediately dip the strip into the solvent. Allow the solvent to migrate to the ink spot line. Developing procedure continued. Do not allow the solvent to reach the end of the strip. Cut the strip at the cut line, producing a bottom section containing the origin and a top section containing the front. Each section in a clean glass tube. Count each section in a well counter and record. Calculate the percentage of impurities in the final result. Basic principles. Radiopharmaceuticals are divided into 2 groups. Chelates, which are solutions, the MDP, DTPA, PYP, and GH, and particulates, which are suspensions of colloids, MAA, and sulfur colloid. Chelate versus particulate. Chelate refers to substance consisting of molecules that bind tightly to metal atoms, Tech, thus forcing the metal atoms to go wherever the chelator goes. Colloids are materials made up of solid particles of such small size that when dispersed in water, they remain in suspension rather than sinking. Chelate's basic rules. Free pertechnetate will always migrate to the solvent front, which is the top. Hydrolyzed reduced Tech always remains at the origin, or the bottom. Bound, the Tech and the compound, migrates depending on the solvent used. Products made with a solution of normal saline migrates with the normal saline to the solvent front. Since products are made in normal saline, they are not soluble in acetone and will remain at the origin. Particulate basic rules. Free pertechnetate always migrates to the solvent front. Hydrolyzed reduced always remains at the origin, or the bottom, and bound always remains at the origin. Here you see the difference. Chelates, the free Tech is at the top, and hydrolyzed reduced is at the bottom. Bound, and it depends. If it was saline, then it goes to the top. If it's made of acetone, then it remains in the bottom. For particulates, they're the same as chelates, except for bound, which always stays at the bottom if it's for the particulates. Chelates. The percent free is equal to the counts on top of the acetone strip divided by the total strip counts so both halves times 100. The percent HR is the counts of the normal saline strip divided by the total strip count times 100. The percent of bound is 100 minus the percent of free plus the percent of HR. For particulates, the percent free is equal to counts on top of the strip divided by the total strip counts times 100. Bound is equal to 100% minus the free. Most of the radiopharmaceuticals that are used in nuclear medicine need to be at 90% tagged value. These exceptions are pertechnetate 95%, sulfocalloid 92%, HMPAO 80%, and DMSA 85%. Chromatography calculations: 95% pertechnetate, 92% sulfocalloid, 90% tetraphosphamine, systemib, PYP, ECD, MAA, disulfiram, meperphanin, MDP, HDP, MAG3, DTPA. Majority of them are 90%. 85% is DMSA and 80% HMPAO. The solvent front is the upper portion of the strip. The origin is the lower portion of the strip. The percent purity, activity of the radionuclide into the desired form divided by the total activity times 100. The percent of impurity is the activity of the radionuclide in the undesired form divided by the total activity times 100. An example of purity: calculate the percent purity of the technetium-99 MAA kit. The TLC strip has been measured in a dose calibrator. The top one, which is the solvent front, is the technetium-99M pertechnetate 5 millicuries, and the bottom is the technetium-99M MAA 65 microcuries in the origin. So you're going to take the 65 and divide it by the 65 plus the 5 and multiply that times 100, so 93% purity. An example of impurity: so calculate the percent tech pertechnetate in the Tech M DTPA kit. The pertechnetate has migrated to the solvent front section of the strip, and the technetium-99M DTPA remains on the origin section. The strip sections have been counted in a well counter. The solvent front has 6,200 counts per minute, where the origin has 884,000 counts per minute. And the background is 120 counts per minute. So we're going to take the 6,200 and minus the 120 counts per minute, and we're going to divide that by the 884,000 counts per minute minus the background, which is the 120 counts per minute, plus the 6,200 minus the 120 counts per minute in the background. And we'll multiply that by 100, and we get 0.7% impurity. Radioassay: dose calibrator quality control. Constancy: performed daily to test the reproducibility of measurements using one long-lived reference source. Accuracy is performed annually to test for activity at the different energy levels using two long-lived reference sources. Linearity: performed quarterly to test for the ability of measure activity accurately over a wide range of values. Geometry is performed only at installation and repair to test for the accuracy of measurements when the sample volumes vary. This can be done by one of two methods. Measurement of radioactivity. This can be done by one of two methods. 1. Put the entire vial into the dose calibrator. 2. Pull up 1 ml of the eluate in an assay, then re-inject into the vial. This second method is used to reduce exposure to the TAC. Biological tests: sterility, apyrogenicity, toxicity. Sterility and aseptic technique. Sterilization is important in pharmaceuticals. Since we are injecting them into living beings, they need to be free of all living organisms, pathogens, or non-pathogens. Every step of the procedure must be aseptic to promote sterility. This includes everything from the formulation of the kits and the containers to the compounding the drugs and pulling up doses, as well as the environment they are made in. Sanitation is not acceptable. Only 75 to 80% is removed. While it will remove some of the possible contaminants, it will not remove some of the more difficult organisms. Methods of sterilization. Autoclaving. It uses steam heated to 121 degrees Celsius at 15 psi above atmospheric pressure for 15 minutes. Membrane filtration uses a 0.22 micrometer filter to remove organisms from the radiopharmaceutical. It is used for products that can't take the heat, such as those containing lipids or blood products. General considerations. Use only sterile disposable syringes and needles. Use each syringe only once. Be careful not to contaminate by touching. This is the most common cause of contamination. Normal saline used in nuke med doesn't contain preservatives and should only be used for one procedure. Wipe surfaces to be pierced by a needle with either an alcohol prep pad or cotton that's soaked in 70% isopropyl alcohol for at least 20 minutes. Control environment when preparing any radiopharmaceutical. The main vehicle for this control is the laminar flow hood. The laminar flow hood does not sterilize anything. It helps to maintain sterility via a particulate-free environment. The hood filters all particles with a size of 0.3 microns or larger, thus providing showers of clean air over the working surface. The hood is only a supplement for a good microbiological technique, not a replacement for it. It keeps air circulating in a certain pattern so dirt and dust doesn't fall into the sterile containers. It works by washing our workspace with purified air, HEPA filters, by blowing off particles. The blower is to be left on at all times. The UV light is turned on only when the hood is not in use, usually at night. It doesn't promote growth. Puncture sites and uncovered needles must be showered in clean air during all manipulations. If the hood is turned off, allow 15 minutes before use after turning it back on. Clean inside the hood using 70% isopropyl alcohol before and after prep and any time spill occurs. Hoods should be disinfected monthly with 10% household bleach. A vertical hood, here you see how the air works and how it flows, where it comes from. The air is intake and it's blown out through the blower, up and out the HEPA filter and exhaust, and down back through the HEPA filter for the air supply. This one happens to have a glass shield on it. You see that in the image. Pyrogen testing. This is done by the manufacturer. Pyrogens are fever-inducing bacteria or fungi. The product must be pure as possible. Types of pyrogen testing. There's the USP rabbit test. Bases the pyrogen test on the temperature response in rabbits within 3 hours after injection of the material. If they get a fever, there is a problem. The dose is equivalent to a human dose based on weight. 8 animals are tested. If no more than 3 out of 8 develop a fever, the drug is pyrogen-free. There's the LAL test, more sophisticated test. LAL stands for limitless ambosite lysate, looking for endotoxin-type pyrogens. Endotoxins can cause diarrhea and toxic shock, based on the formation of an opaque gel by pyrogens. Sample is incubated at 37 degrees Celsius. The more gel that is accumulated, the more pyrogens there are. Toxicity. Therefore, a radiopharmaceutical is approved for human use. Its toxic effect and safe dosage need to be established. These tests can be carried out in various animals. We now use cell culture and computed modeling instead. Using at least 2 different species, the dosage at which 50% mortality of the animals is observed in 60 days following the administration. Lethal dose is 50-60. Usually, toxicity arises from the pharmaceutical part, not the radionuclide part. The end.